We talked a little bit about forces last week, right? Okay. Did we talk about sum of forces and net forces? Talk a little bit about that. Okay. Let's did we talk about free body diagrams? Everyone, what's a free body diagram? Talk to me about what a free body diagram is.
It's like the net force would be for no.
Give me what's a free body diagram.
It's like the square with the arrows coming out which direction.
Closer. Okay. Let's look at our list of when we try to solve a problem. What's our first thing? What's our first thing? We look at draw a picture, okay? When we talk about a free body diagram, this is important. A free body diagram, you should all be able to know what this is and do it. A free body diagram is a simple representation, a drawing, that represents all of the forces on an object. Okay? So I could have some really interesting, elaborate object, okay, that's got, all these different things on it. It's got some other thing. It's got some gears, whatever it is. And I got a bunch of forces on it, right? Whatever this object is, okay? And I got force 1 and force 2 and force 3. I want to draw this simply, okay? So what I do is it's called a free body diagram. That free body diagram means simply a simple representation. That simple representation could be a square. Simple representation could be a circle. It doesn't matter. But it's some sort of simple representation, and it shows me all the forces. So it says, here's my force 1. Here is my force 2. Here is my force 3. It shows you all. So this guy right here, guys, this guy right there, get rid of this. This guy right here, this is the free body diagram. Free body diagram. It's a free body, meaning it's sitting in space, it's free, it's a body, the block is a body, and this is the diagram. And so it's showing you all the forces. Free body diagram. If I ask you to draw that, that's what you're going to do. Does that make sense? What did I say? What did I say the free body diagram is? There you go. If there are three, then you would draw 3. If there are 2, you would draw 2. If there are 20 million, you would be here all year drawing all 20 million. Okay? Make sense? Okay. Now, so let's do this as an example. Okay, let's say I have said crate, right? You all know I love my crates. Maybe you don't, but you will know that I love my crates. Okay. My wooden crate. Right. Okay. So I've got my wooden crate. And I can go through and draw my green. All right, so I've got my crate. All right. Now, this crate, let's say that this crate is sitting out on a dock somewhere, okay? Because it's going to get taken off the ship. Taken off the ship and we're getting moved because this is from Tasmania. And what does that mean it's inside? Taz is inside, right? This little Tasmanian devils inside there trying to get out, right? No. Tasmanian devil, does everyone know? No one watches the cartoons Tasmanian devil? Yes. Do we have to go and look up the Tasmanian devil cartoon? Here. Right? Did I lose my internet?
Please tell me this class is recorded.
It is totally recorded. Well, anyway, for those of you who don't know Tasmanian Devil, go watch some more cartoons. Your homework is to watch cartoons. Okay, so let's say that this crate is on a rope. Okay, it's on a rope. All right, so it's a rope, right? Okay, So there's a rope, there's a crate. What are my basic forces? Gravity. Where does gravity go? Down. So there's a force of gravity down. What else is a force? Where else?
The rope pulling back up.
Okay, so there's a force. I'm going to call it force T. And let me explain to you why I call it force T. Force T, T for tension. Okay? Rope has tension in it. What does tension mean? Someone talk about tension.
Stress on the object.
It's not taking a test. Yes, right. I get that. No, but give me some more. Yes, you're right, but give me some more detail. Give me some more. What do you mean?
Like it's defending direction.
What would be the opposite of tension?
Slack.
No.
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 Relaxation.
No. Okay. If I have a rope, if I have an object. It doesn't matter what the object is. And I have forces acting on either end of the rope or this object. Let's say this object is in tension. What direction are the forces? Horizontal. Outward. So there's a force out this direction, and if the object is not moving, there must be a force where?
On the other side.
The other side. When I'm pulling things apart, I am in tension. Think about from the forces standpoint. What would be the opposite of What would be the opposite of the scenario with the forces?
Pushing inwards.
Pushing, and it's called compression. Exactly. Okay. So when we talk about objects being in tension, the opposite. This is tension. This is compression. But to your terms, Keaton and Charlie, if I put a rope in compression, what happens?
You get slack.
You get slack. Because can the rope work in compression?
No.
No. Ropes only work in tension. They do not work in compression. So when you think about cable bridges, suspension bridges, all of those cables have to be designed so that they're in tension. You've probably at some point tied some really complex something or other, a bunch of rope, thinking you're going to get all the lines in tension, and somewhere one of the lines is slack. Okay, that's because the way the forces add up, you end up putting compression on that piece of rope. And we'll do an example of that at some point. But the idea here is that tension is pulling apart, compression is going in. An object has to work, in order for the object to deal with the forces, it has to work in both of those directions. Rope only works in compression, in tension, not compression. A column or a piece of steel wire can work in both tension and compression. Okay? But at a certain point, that steel wire may bend or what's called buckle. When the steel wire does one of these things, or when you try and push on it, okay? That's called buckling. Okay? I'm totally going to misspell this. Buckle. I think it's how you spell it. Buckling. If you look above you, the lights are on those ropes, those wires. Those wires are in what are those wires exhibiting? Tension or compression? Tension, okay? You see the three beams above the main center beam here, right? You see that? What are those beams? Can you take a guess as to what those beams are in?
Compression.
Well, some of them might be in tension, some of them might be in compression. It really depends. My guess actually is that the two angular beams are in compression while the middle beam might be in tension. The vertical might be in tension. It really depends. And you can do the calculations when you do this. In one of your first years in engineering school, you do that. But it really depends on the total forces. But some of those beams can be in compression, can be in tension. Also depends on the load that's being applied. If you apply load in a different location, you might change the tension and compression. But because those beams can handle both tension and compression, it means that maybe that setup is set to maybe at some points those beams might be in tension or compression. It's set up to possibly change the shift the thing. Because if the middle one was in tension, you put it as a rope or a wire, then if it was in compression, it would be useless. Yes, sir.
Wouldn't it be in compression because like you've got the weight coming down from the ceiling, so that's pushing down, and then you've got like as far as the beam's concerned, you've got the cross beam.
Well, here.
So you got basically you know like.
I know what you're saying. You have to do the calculations. There's an assumption there, but you have to do the calculations because let's say the forces are coming inward and down. Let's draw that. So everyone can see what we're talking about. We have a beam here, right? And then we've got a beam here. We have a beam here, right? And then we've got a beam here. They're all coming in pretty much to the same point, okay? If the roof is up above. If say the force is in this direction, right? And let's say the force is in this direction, correct? There's a possibility that the actual force is this direction here. If this is pushing down, then it's actually pulling, and therefore there's a pull at the top. So we're actually potentially causing this to be in tension. This could be in compression, and that might be in tension. Right? But if the load changes, maybe that this becomes in tension and that becomes in compression. It really depends on the wind load, if there's snow on the roof. It really all depends. Okay? But you have to know that. You're right. There's an assumption there, but that's why you have to do the calculations. Okay. All right. So there are those three forces. So if I'm going to draw, so everyone do me a favor really fast. Draw me the free body diagram. Draw a free body diagram for this Tasmanian devil crate. Do it. You got 30 seconds. Go, 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 go. Quick. Everyone needs to draw an example and show me. Hold it up. When you're done, hold it up. Nope. That's not a free body diagram.
Well, can you further explain what a free body diagram is?
Free body diagram is a simplified version.
Okay.
Simplified version. Yes, we're close, Keaton. We're close. This is very simple. I get it. But I want you to all draw a free body diagram. I want to see it. Let's see it. Beautiful. Okay. Where's your forces? Okay. That's good. That's good. So let's look. Okay. Does everyone draw one? Everyone draw it. Michael, you got it. You guys got it. Okay. You guys got it. Okay. Everyone look at Courtney's for a second. Where are Courtney's forces?
On the bottom.
So Courtney has a box like this, and Courtney, you drew what? The force of gravity here, and where'd you put the force of tension? Next to it. Force of tension. Now, Faith, where'd you put yours?
Force of tension on the top, gravity on the bottom.
Okay. Force of tension on the top, and the force of gravity on the bottom. Now look, Faith's is probably a little more intuitive than Courtney's. That's okay. However, there technically is nothing wrong with either of them. The tension is on the top of that object, and that's probably the better way to do it. But as I stated before, there is no difference. Technically, this is still correct because I'm pushing up or going. That force is in the opposite direction of my gravity. Does that make sense? Because again, those vectors can be moved around. Clear? Yes? Yes? Okay. Now, we're going to throw a wrench into this a little bit. Okay? Let's say this Tasmanian box, okay? So let me ask you a question before I even go there. So we know that we've got two forces, and what can we do with this? If we're going to try and solve a problem, what would we want to do with these forces? We want to know the motion of this box. What would we want to do with these forces? Think of it simply, right? Why would we want to add them together?
Because that's you get like a net force,
And what does that net force tell you?
whether it's moving or not.
Okay, well, it tells you not whether it's moving or not, but whether it's accelerating or not.
Yeah, sure.
Let's be clear about that. If I want to know if this box is accelerating or not, I need to add the forces. Let's look at that. The sum of the forces is equal to my F of tension plus my F of gravity. Okay? Let's assume that the force of gravity Let's assume that f of g equals negative 100 newtons. Okay? So let's say that the forces are balanced. That means the sum of the forces equals to negative 100 newtons. Why is the force of gravity negative? Down. And if they were balanced, what would the force of tension be? Everybody? Hello? What would it be if it was balanced? 100 newtons. What's the sum of the forces? Zero what? Okay. Let's do this for me. Let's go back into the very top. The sum of the forces in variable form, what's the variable? When we add them together, what do we equal? What is the sum of the forces equal in variables? Well, net force, it's going to be a net force, but what does a net force equal?
0.
No, I said in variables.
FT plus.
What does F equal? What does F equal?
Oh, mass times acceleration.
Okay, so there's a mass times the net acceleration. Let me draw that bigger so we can actually. It's the mass times the net acceleration. That's our net force or our sum of forces. Sum of forces, net force, same thing. Okay? But it means we've got a mass times the net acceleration. Okay? The mass, is the mass going to go to 0? If my sum of my net forces, sum of forces is 0, is my mass 0? No. What's 0? My acceleration. That means I'm not accelerating. Does it mean that I'm not moving? This is very important. Do you guys understand this? Even though my acceleration is 0, what kind of motion do I have if I have 0 acceleration, possibly? Constant velocity. Exactly. Well, I always have constant velocity. Whether that velocity is 0 or some negative or positive number. Okay? You have to envision this. There's an example, okay? Let me give you another example. If I've got that crate, okay, I'm going to draw it real simple here, and I've got my rope, right? Here's my rope, okay? Right, and here's the ground, okay? Let's say the object is moving up. It's going up, right? But the velocity of the object is 5 meters a second, positive, constant. What does it mean? If my velocity is constant, what does it mean about the forces on this crate? They equal 0. So what two forces do I have? What two forces do I have on the crate? Gravity and tension from the rope. And even though I've got velocity of constant 5 meters a second, what's my acceleration of the crate? Equals 0, right? That means that my total force, my net force, must equal mass times acceleration. And if acceleration is 0, that means my net force is 0. And if I know my gravity, F of g, then F of t must equal F of g. Now, why is it not equal the opposite of F of g? Because the opposite comes in when I sum them. The sum of the forces is equal to Ft plus Fg, and that equals 0, which means that number has to be negative if that number is positive, right? I want to be clear on the math here. Do you see that? What I'm getting at is that F of t is equal, if F of g is negative 100, then F of t must be 100. So if it's, if F of g is 100 newtons downward, then F of t must be 100 newtons upward. But when I put them on the other side and I say sum to equal 0, that's where the negative sign comes in. You guys see that? No? Do you see what I'm saying? This is positive 5 meters per second. And I'm just saying, if it's a constant velocity, Paulina, if it's a constant velocity, then the acceleration is 0. Right? Because if it's constant, that means velocity final minus velocity initial over my delta time is equal to 0 over my delta time, right? And that's equal to my acceleration, right? Yeah. Because velocity final and velocity initial are the same if it's constant, right? I'm 5 meters a second at the beginning of time, I'm 5 meters a second at the end of time. 5 minus 5 is 0. Right? So all of this is to explain that even though I have forces on here, and my acceleration is 0, even in that case, even though I have an acceleration of 0, I can still be moving. Does that make sense? This is a really important piece. I want to make sure everyone gets that. Questions? Drew, Gabe, questions?
No.
Okay. All right. Do you understand what I did here with the math? Why I have f of t equals f of g, not f of t equals negative f of g. Do you understand that? No, yes?
Yeah, I understand what you're saying, but I'm still confused because like f of t doesn't equal f of g. F of t
It does as an absolute value.
as an absolute value, yeah.
Yes. When they're on the same side of the equation, then they are opposite of each other. Once you flip the side of the equation, then the signs become opposite, right?
Oh yeah.
You see what I'm saying?
Yes, I
So you have to start with this, and this is a confusing point, and it's kind of arbitrary, right? Like I could say f of t equals opposite f of g, but then my sum of forces is going to be 0.
Yeah, I get you. That makes more sense.
Okay, so start here. Sum of the forces are equal to 0, and that means my positive f of t must equal my negative f of g, so that when I flip it to the other side, then I can get this. Does everyone see that? Okay. All right. Important stuff. All right. Let me throw a wrench into this. Okay. So now, rather than my crate being moved in midair, let's do this. Let's assume it's on the ground, about to be lifted. It's about to be lifted. Okay. Let's assume in this case, f of g is negative 100 newtons. But this time, f of t is going to equal 80 newtons. What does that mean about my sum of forces? Let's look at that. So if I have 80 newtons up minus 100 newtons, how much force is left over? How much? Negative 20 newtons. Let's think about what that means. What does that mean? Yes, ma'am.
How do you know if like f of t or f of g goes, or like how do you know where to plug it in? Because what if it's like a different force? Do you know what I'm saying?
No.
But where you have like the sum of f equals ft plus fg.
Mm-hmm.
Is that always like that?
It's always going to be like this. Okay? If I have my free body diagram, okay, and we said we've got f of g and f of t. The sum of the forces it's just summing up the forces on there. So f of t plus f of g. Now f of g happens to be negative, right? And f of t happens, we're just going to sum that up.
Okay, but I'm just
Okay? Let's say I had, and by the way, and let's be very clear about this, these forces are in what direction? They're up and down. They're vertical, right? We're only doing vertical. If I had, let's do this really fast. When I say sum of forces, I really am, when I'm talking about in this example, I'm talking about sum of forces in the y direction. Okay? Let's say I had another force here, f of 1. What are the sum of the forces in the y direction on this free body diagram? Well, just list them out. Make the equation. Plus f of 1. It's that simple.
so you just like add
You
the
just-
other one in there too.
When we say the sum of the forces, that we just mean all of the forces acting on that body. Add them up. Let the values determine their sign. Say, notice I have f of g is negative, but I still put plus.
Yeah.
The value will be negative, will come out. But the thing is, if I had this, let's say I had f2, can I put f2 in this equation here? Why not?
It's all wide.
All in Y. Well, not only that, we've determined, let's think of it even beyond that. Let's say I didn't say f of y, right? You can see that these are all the y directions. Can I put f of 2 here? Because what? Not just because it's f of y. Why can't I add a horizontal force to a vertical force? Right. For the same reason that gravity only acts vertically and doesn't act on an object horizontally, I can't add gravity to the horizontal motion. Therefore, I can't add horizontal motion or horizontal forces to the vertical. So you've got to treat these independently, your horizontal and your vertical. Does that make sense? Everyone clear on that? So back to Courtney's question, whatever forces you have on here, you add up. But you can only add them in the f and the y. So you'd actually have to make two sum of forces, some of the forces in the y, and then some of the forces in the x, equals F2. Does that make sense? With me? Paulina? We're on the same thing. We're on the same thing. I'm just giving you an example. Courtney's question was this. Well, how did I know that f of t and f of g are summed up? And all I'm saying is that when you have your free body diagram, all you're doing is you're summing up the different forces. But you can only sum up the forces in the same, I say direction, meaning up and down versus left and right, right? I can add positive and negative vertical. I can only add my verticals and only add my horizontals. Can't add them together. Does that make sense? Gotta split them up. Keaton, you with me? Keaton, I'm over here, not outside. Okay. All right. Cool. Make sense? All right. So let's deal with this. So now, here's the thing. So back to our original problem here. We've added the floor here, and we said our force of the rope is 80 newtons, and our force of gravity is negative 100. Let's forget the math for a moment. Let's forget this equation for a moment. Let's just think about this. I have 100 newtons down and I have 80 newtons up. What's happening to the box? There's ground here. Is it moving anywhere? No. Why not?
There's not enough force.
Okay, there's not enough force up to lift it up. Okay, there's not enough force to lift it up. Okay? So, I have a difference of 20 newtons. What does that mean? What does that mean? It's a little bit of a jump. You got to think back to last Friday. Where's that 20 newtons? Hint, 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 hint. My sum of forces are always going to equal, well, take that back. Never mind. Scratch that. What is this extra 20 newtons? What is that negative 20 newtons? What does that mean?
It means that negative 20 newtons means that the 80 newtons of the tension of the rope are being canceled out by the 80 newtons of the force of gravity, but there's an extra 20 newtons of the force of gravity, which means the box is going down.
But we're on the ground. Is the box really going down? No. So what must be stopping it from going down?
Force of the ground.
Force of the ground. And how much is the ground pushing back up? Okay. This is important. There is an additional force called the normal force. It is the force the ground is pushing back perpendicularly to the object. So what I end up happening is I have the sum of the forces equals my force of my tension plus my force of gravity plus my force normal. Then it could, if it's not moving, then it's zero. There's a question here. The normal force is kind of like the fudge factor force, okay? It's a force that possibly exists. When does this normal force not exist anymore?
When the net force is zero.
When what?
The net force is zero.
Well, the net force is of what two things? Right now, the net force is zero.
The tension in the direction.
When tension equals gravity. And when the box is what? On the ground or off the ground? Off the ground, or there is no force necessarily from the floor pushing back. So let's think about this, okay? Think about yourself on a scale. Okay, somewhere I have a scale. Somewhere I have a scale. Oh, look, I got a scale. Okay, I need a volunteer. Volunteer. Okay, you need you to stay on the scale. Someone who's okay saying this stuff. You can change. Okay. All right, now, here's what I'm going to do, okay? I'm going to pick you up. Can you feel that? Okay, lift your arms. Okay, now. All right. See if I can do this. Okay, so what's your weight right now? Are you
98.
how much?
98.
Okay, so she's 90. So right now her force going down is 98 pounds, right? Okay. I'm going to lift up. What is her weight?
Still not moving.
No,
Oh, 70.
70. Okay. What else? What's it now? 40.
20, 10, 0.
0. Okay. Okay. So the normal force. Where's the normal force in this? Let's talk about this example with that. What's happening? Talk to me about what was going on.
Your force was
Related to the crate.
you were the rope.
I'm the rope pulling up.
Yeah.
Anika is the
Off.
crate. Sorry. And where is the normal force? What's the scale pushing up. At a certain point, that scale reads what?
0.
When does that scale read 0?
Your force the force of gravity, or like your force,
My lift force equals
the force of gravity coming down.
her weight going down, her force of gravity, her weight going down. I can apply less than her weight, and she goes from 100 to 70, right? Or 90 to 70. And apply a little bit, that goes to 40. That's the leftover. Does that make sense? Now that means that the ground is pushing back, needs to push back on her less than it originally. Right now the ground's having to push back a lot. When I lift up, the ground's pushing back less. Does that make sense? Everyone clear on that example?
Is it birthday? Now I'm 95.
Well, you just did Okay, does that make sense, guys? So the normal force is the force pushing back on the object from the ground. Okay? But let's just make this one caveat. I need to make this one caveat. Again, that normal force is perpendicular to the floor. Okay? Let me give you an example of what this means. If I had my box, okay, and I had my floor, okay, what are my forces right now?
Gravity.
I have force of gravity, the ground pushing back up, which is called the normal force. Right now, what is the force? If it's standing still, what does the normal force equal?
Force of gravity.
Force of gravity, right? What if, however, and we'll talk about this a little bit. What if the box was at an angle? Which direction does gravity push? Downward, okay? It's the force of gravity. But the normal force is the force pushing back perpendicular to the object. So that force is this direction. Okay? I'm going to talk about whether we may do a very basic problem in this. I get more complicated in this with the honors group. But right now, I want you to understand that the normal force is always the force pushing back perpendicular to the object. Let's talk about this for a second. What does this mean? Let's think about this physically, okay? If I have an object.
Scrubbing bubble.
Oh, let's do that. That's probably better use. Right now, okay, can you hold that in? Okay, just hold it still. Right now, scrubbing bubbles is sitting. You can like just one. Right now, scrubbing bubbles is sitting on the ruler. Okay. How much force is the ruler pushing back on scrubbing bubbles?
The same amount as gravity.
Okay. Now, what's going to happen at some point?
It's
It's going to start to slide. Well, why is it going to start to slide?
Because force of gravity is increasing.
Well, not force of gravity is increasing.
But the normal
But the normal force is getting less and less and less.
Alright,